Hello, everyone. Thank you for joining me again today as we work through our fundamentals of the electric grid. This is the second part in our introductory three-part series, which overall is going to be a series on electric resource planning. So I'm going to go ahead and start moving us through the material. And as I say, this will be a bit more of a technical discussion today, although we're going to break it down so everyone can follow along. Just a quick note for us as well. My name is Andrew Kramer. I lead Ulteig's resource planning series, uh, resource planning team, I should say. In this series, we're going to discuss a lot of things such as energy market modeling, integrated resource planning, rates and tariffs, all these good things, which also relate to our services. If you're interested in maybe learning a little bit more about this overall series or education, or perhaps Ulteig services, please, my email address is listed right here on this slide. We'll also be listening down below in the YouTube, and also add me on LinkedIn as well. I love to converse and just talk topics. It doesn't have to be all business. So maybe, as I say, you just want to share ideas and collaborate. Please reach out to me. We're always happy to schedule a sit down and introduction meeting if anyone would like that. But with that said, let's go ahead and jump into today's material. Today, we're going to go ahead and look at a very brief history of the electric grid. I think it's hard to understand how the grid operates today unless we understand a little bit of its history. We're going to reinforce a few of our concepts in the first discussion, such as AC versus DC. We'll dive into a little bit more detail on that today. And we're also going to introduce concepts such as reactive and power factor, which are pretty important to the electric grid. We'll keep it a high level again for maybe those more on the business side. But as I say, on the engineering side, you might learn something as well. So please pay attention to those particular points and let us know if you have any questions on it in the comments below. We'll also discuss grid frequency and frequency restoration. This is actually how the grid operates in terms of cycles. We'll talk a little bit about that. A little bit confusing if you've never seen it before, but I think we'll be able to break it down so everyone can follow along. So let's go ahead and jump through our history and our first point, which is, I say, a brief history of the electric grid. You know, it's hard to determine where to start when we talk about electricity, right? A lot of the original research on it, you could argue, dates back to ancient times. The Greeks and a lot of the other ones had certainly understood magnets and, understood that they were an interesting phenomena. The 17th century, a whole lot of work was being done on electricity and the startings of the theory behind it. But for our purposes in electric resource planning, we're going to go ahead and talk about the era when electricity was used by customers as a competing resource, as an example against oil lamps and things along those lines. And a good place to start is probably Thomas Edison's Pearl Street Generation Station, which is regarded as the world's first commercial electricity plant. I believe it was primarily coal-based at the start, and it served a very limited number of customers early on for just lighting. So as I say, it was a pretty small generation station. There weren't, any other ones out there to help you. And as I say, it was pretty much just this one little gen station. So when it needed to go into maintenance or something along those lines, all of your light bulbs would stop working in this early phase. So let's go ahead and jump to just a little bit more of the history on this. The early electric grid wasn't regulated or interconnected in the traditional sense. Typically, electric systems become more reliable when more generators are interconnected. This allows elements of the system to lean on each other during times of need. There's a famous display, or I should say ride, I guess you might call it, down in Disney World called the Carousel of Progress. And it kind of takes you through a family in the United States as time evolved. And I was pretty young when I saw this, and it made an impression on me. Dad's sitting in the living room, and he's got all of these wires hooked up all over the place. There's wires for different voltages. Nothing was standardized. And, Dad's kind of playing around, and he hooks up an extra load more than he should, and he shorts out the whole neighborhood. And you can hear, just this big pop. And as they say, he takes out one of the key circuit elements in that neighborhood, and the whole neighborhood's out of electricity at that point. That was not an uncommon occurrence. Again, a little bit of comedy from Disney at that point, but it certainly wasn't uncommon for a single generator to go down and everybody loses power. When you are not interconnected, that is the logical resource when there is an outage. Just as I say, everybody sits around waiting for the lights to come on because there's no other generators to lean on at that point. So, in addition, at this time period, it's kind of worthwhile to note that we hadn't fully determined yet whether we're going to be using alternating or direct current. A lot of the early work and generators that were being put out by Edison's company were DC based. We're going to go and step through very quickly here the War of the Currents, which is kind of an exciting time in history right now, or was an exciting time in history, I should say. In this time period, as I say, we weren't decided whether we were going to be based on alternating current or direct current. A lot of one of the original champions of DC current was Thomas Edison. Who worked for him at that point was Nikola Tesla, who's pictured in this picture above. He was actually working for Thomas Edison at that point, and he ended up believing that alternating current was the way of the future. There's a lot of history here. As I say, Nikola Tesla worked for Thomas Edison at one point, and there was a severe fallout between the two of them. Rumor has it, or as legend would say, I should say, supposedly Nikola Tesla was actually digging ditches at one point because he said he would much rather do that than actually work for Thomas Edison. That's how much they despised each other. Another colorful story put out by Nikola Tesla, which very much may have been true, was that supposedly Thomas Edison didn't actually like alternating current because he couldn't understand the more complicated mathematics associated with it, the wave equations and everything else. So we end up with two competing camps. We have Nikola Tesla supporting AC, who ended up being backed by Westinghouse. That's the famous Westinghouse generator. And then Thomas Edison, whose companies who backed DC that would eventually go on to form General Electric. That was well after, I think General Electric, the name of that came well to be after Thomas Edison was removed from the whole operation. So in this early phase, again, we have direct current championed by Edison and alternating current championed by Nikola Tesla. It was a really famous battle that was waged for market share between the two of them, and it all came to a head at the Chicago World's Fair, where Nikola Tesla and Westinghouse underbid and beat out Thomas Edison due to the advantages and the cost effectiveness of alternating current. As to say, it was a really neat time period too, because along with this dramatic backdrop of lighting up the World Fair, you also had crazy things going on. I guess there was a serial killer that was luring people into his murder castle by name of the gentleman was H.H. Holmes. It's a famous book that's out related to this. I've never read it, but I know people that have. Supposedly it's quite good, called Devil in the White City. It covers a lot of this era. There's a little bit of historical fiction in it because it enters into the mind of H.H. Holmes, but it's also very well researched. There's a whole lot of literature in this era, and I'd invite you to look into it just because it really does show how the grid came to be. And at this point, as I say, it was really the Wild West of electricity. There were no regulations. You could pretty much do what you want. So as I say, how we actually got to where we are today is just an interesting story, and I'd invite you to look into more of that. Okay, so we've talked a little bit about AC and how it went out. But let's talk about specifically why. What are the advantages of AC? We've talked a little bit about this last time, and I just want to reinforce it before we start talking about some of the nuances of it. AC has some distinct advantages over DC. It's easy to what we call step up with transformers, so it's very easy to increase voltage. And as we learned last time, a higher voltage typically means less thermal losses relative to higher current. That was those V squared over R versus I squared times R. The other thing is, again, we've mentioned last time, is AC, you can put things like multiple phases in it, which allows for the elimination of the return wire in a more effective, more efficient form of power transfer. So we've touched upon this a little bit last time, but again, I just want to reinforce some of the reasons why AC actually was the winner and why it made the most sense from an economic standpoint. Now, like all things, if we make a choice, it's got a price associated with it, right? So let's go ahead and dive into now what are the results of us choosing to go with a system based upon alternating current. So as we say, AC has a price associated with it. The electric systems are built around the speed at which the AC grid cycles, right? So again, we talked about it last time. Your power going into your light bulb is actually going up and down. It's 60 cycles per second, so it's actually pretty fast. That's why you don't actually see it. What we have here is a 60 and 50 hertz cycle. Parts of Europe and other areas in the world operate at 50 hertz. The US grid operates at 60 hertz. Deviations from frequency of 60 hertz can trip electrical equipment offline or even damage it. Okay, so the way we work in terms of the control mechanisms in the United States is based upon frequency. So deviating a whole lot from 60 hertz is not a good thing, or even frankly, a minor amount. Sometimes things like programmable logic controllers are very susceptible to small fluctuations in frequency. We have to be very careful, especially for heavy industrial loads, which can be very susceptible and tuned to specific frequencies. If the frequency drops too much, the whole electric grid can collapse. So that's pretty much where you know the grid itself can be in major trouble. It's when you're watching the frequency and you start to see it drift below. You might think and look at the sometimes like maybe you've seen your lights flickering or something along those lines, and you think, oh, that means the frequency's dropping. If the grid actually dropped to that point where you could see that much flickering, it would have collapsed. That's actually a local phenomena often associated with voltage. So normally, as I say, when you start to get below 60 hertz, even a small amount, 59.99 or some 59.9, a lot of times that means the grid itself can be in trouble. So this leads to things like load shed, where we try to get rid of load to get the frequency back up, and things along those lines as well. So this goes into all the control centers in the utility rooms and what they're trying to do under emergency conditions to restore frequency. We'll talk about this in just a little bit in terms of how the system responds when there is a frequency deviation. So the need for reactive power. Another price of using AC current is that we have something called reactive power coming on into the situation. Motors and other electrical and electromechanical devices require set voltages. Voltage is a measurement of the potential to push power down the lines, as we've seen before. Deviations from this voltage can cause issues or potentially damage equipment. So again, frequency deviations are bad, voltage deviations are bad. To maintain voltage, you need real power and reactive power. This term real and reactive are horrible. I'll explain a little bit why we use them. But again, I don't want you to think that reactive is a lesser form of power or an imaginary form of power that's not real or not measurable. Both are real things that we can measure on an electric system. To make things even a little bit more complicated, reactive power, when we deal with the mathematics, has an imaginary number in front of it. That's just how we treat it mathematically. That does not mean that we cannot measure it or it is not quote unquote real. So I don't want you to think that real power is any more real than reactive. That term real, again, just relates to the fact that's how we track it in terms of the mathematics when we actually deal with the theory behind this. Both of these are measurable things that we can account for on the electric grid. And I want to give you a little bit of a picture for what reactive power is here. A common analogy of reactive power is that it is the quote unquote foam on the top of the beer. I don't like this analogy. I know why it's used. I don't disrespect anyone that tries to make the analogy. It's not terrible for an introduction, trying to give you a picture of what it is. But I think it's confusing in the fact that you might think, well, foam is not, real. It just dissipates, and that's reactive power. That's not the case at all. Reactive power is a very real form of energy. And what it actually is that when you consider all the motors and the parts and everything else on the electric grid, we store energy in both magnetic and both electric fields, I should say. And what reactive power is that energy that's sloshing back and forth between the electric and magnetic fields. Being stored, it's not being used. All it is to say, you can imagine almost kind of like a water tower where we're storing that water. We're storing that energy and it just gets sloshed back and forth between the electrical and magnetic parts of the device. Very important for motors and other electric devices that we have that accounted for. Another thing that oftentimes confused is, well, that means reactive power is really not using up any energy. That's actually not true, because as we increase the reactive power, we also increase the quote unquote the real power, which is associated with thermal losses. So in many respects, the reactive power, how we do account for it is a matter of bookkeeping in the mathematics. But as I say, increasing reactive power does actually lead to more real thermal losses as well. So let's talk about how we track this. This is called power factor. It's very famous. This is kind of electrical engineering 101. Everybody looks at power factor at some point when you go through an electrical engineering course. Generator owners do not like producing reactive power, as it takes away from their real power sales, right? So energy that's being stored in field is not really something I'm selling you, the customer. I don't really like to have to produce that. So how do I keep track of this? A convenient way is called power factor. What we utilities will often charge you if you're using lots of reactive power. So a way to mitigate this is to actually install physical equipment like cap banks that will bring you more on your side of the meter, so you are using less reactive and just consuming more real. It's a way of mitigating, as I say, so the utility doesn't have to deal with you. A way the utility keeps track of this, again, is called power factor, which tells you, it's that little triangle on the bottom, how much real power you're using relative to the reactive power. And that's the sum of which is called the S, or the apparent power again. So that power factor is pretty important. It can be used to assess penalty factors and everything else on your bill. Typically, that's more relevant if you're an industrial or potentially commercial customers, is where that enters in. Residential customers are typically charged kind of a hidden rate in their bills, kind of a blended average across the whole system. It would be very unusual for a residential customer to be using large amounts of reactive. Okay, so we've talked a little bit about reactive. Let's go and go on to frequency. We mentioned that just a little bit ago, 60 hertz, right? So the United States electric grid is divided into three zones, which are sunk together in terms of AC shapes. When we get into the discussions on the independent system operators and the grid and how we control it, we're going to spend a lot more time on this. But for right now, you can think of the grid being divided into three independent regions. There's the Eastern Area Interconnection, which is that blue region on the right. There is WEC, the Western Area, which is in red. And then finally, we have parts of Texas, which is ERCOT, or the Electricity Reliability Council of Texas interconnection. All the generators in these regions step together. You can think of them all working together in sync to preserve system reliability. It is a fact that interconnected systems with many maintained generators are more reliable than disparate systems where generators cannot rely on each other during times of need. Again, we gave that example in the early electric system where one generator or maybe two generators trips offline and blacks out a whole neighborhood. Typically now, unless there's an issue with like the local distribution system, that doesn't happen, right? I can lose a coal plant somewhere. I can allow my solar facility to have clouds moving over, dramatically reducing output, right? We don't black the grid out. It's because all of our generators in a region step together and work together to preserve frequency. Spend a little bit of time here now on how frequency relates to all the stuff on the reliability side. Preserving frequency in the United States, this is done by what we call tie line bias control. The control mechanism used in the United States to maintain frequency, again, is called tie line bias control. The calculated area control error, also known as ACE, is used to implement tie line bias control and is a way to quantify the instantaneous health of the system in terms of scheduled versus actual net interchange in frequency. The control performance standards, CPS 1 and 2, measures the health of the system over a time period. And we'll go into this a little bit just on the next slide, give you a physical picture for what happens here. With tie line bias control, frequency is the control metric used rather than load. Deviations from scheduled frequency are due to what we call unscheduled flows. So again, a picture of ACE might be, just trying to give you kind of a medical analogy. If you eat an apple that's good for you, we might say your ACE looks very healthy. However, if you've been eating nothing but sugar and candy for the last week, your control performance standard may be very negative. So ACE tells you kind of instantly what you're doing, and then the control performance standard tell you how much your frequency is deviating from 60 hertz on a longer term. Both of which are very important, right? Obviously, in terms of a short-term look, if I get a major deviation from 60 hertz, I can collapse the grid. Over the long term, though, we don't want lots of deviations. That's not good either. We need to keep track how good we're doing to make sure we're roughly in line with 60 hertz. That's the control performance standards. We'll spend more time on these as we get into some of these more specific discussions on frequency in the future. So generators working together to preserve frequency. The amount of energy from generators that works together in an interconnection is staggering. I mean, you can just picture all the solar facilities, batteries, coal plants, nuclear plants, gas turbines, pumped storage, geothermal. I mean, that's a whole lot of these guys. They're electromechanical devices and all sunk together, given the mass. You have to picture how big some of these things are. They're the equivalent of electric freight trains. And woe be it to the generator that tries to step in out of step with the other generators. A good analogy is running a train into a mountain. Again, these are mechanical devices. These are rotating masses. In the case of a solar facility, it's less interesting. You might just blow out an inverter if you try to sink it out of step or potentially damage the panels. I actually heard stories when I was in the utilities back in the day of, in the old days, you would watch this waveform, the 60 hertz 60 hertz moving up and down. And they had something called a synchroscope. And in the control center, they would actually try to manually line up the waveform and hit a button and put it in. Now, if you're out of phase by 180 degrees, again, that's the exact opposite of where you want to be in terms of the waveform. That's the equivalent of your generators stepping in front of a freight train. All the generators working together, a huge amount of energy associated with them. I've heard stories of, and I don't think they're, kind of old, wives' tales, you might say, and legends passed down. This did actually happen at various points of generators being thrown at 180 degrees out of phase, and the generator literally trying to rip itself off the foundation of the building to try to force itself back in step. Again, it's the equivalent of stepping into stepping in front of a freight train. So again, there is a lot of this is heavily automated now, like the synchroscopes and everything else are designed so you can't do that anymore. But I wanted to give you kind of that picture of what happens with the amount of energy and everything else that's stored on the system, or I should say in use by the system, and how all of these generators working together do produce a giant freight train that work together, and you have to be brought in step. So let's talk about what happens when we drop below 60 hertz. What do the generators do? It's a little known fact that too much generation is just as bad as too little generation. If we have too much generation online, we're go above 60 hertz. That can cause the grid to collapse. But more often than not, what happens is generators trip offline, and that leads to under frequency, where we're actually reduced below 60 hertz. The criteria for how systems respond and balance are detailed in the NERC BAL standard. So you can go to Google and look that up online if you want more information. When a system overgenerates, frequency goes above 60 hertz. When it undergenerates, frequency goes below 60 hertz, again, as we just mentioned. A very common occurrence is when a thermal generator or series of thermal generating units, quote unquote, trips. That means they go offline. Something happens, they say, where the generators just have to shut that down. This leads to a generator unplanned generator outage and load exceeding generation. When this occurs, the resources on the systems work to restore frequency, and they all work together to do it. Again, think of the freight train. That's what's going to go on. They're all going to work together and get their speed back up. So this is a disturbance, and this is actually a historical disturbance that was analyzed by our friends at NERC. So I took this mostly, as I say, from the NERC, some of the NERC reference material. Again, the reference is below if you'd like to look in more here. And what happens, this was an area in WEC, and we're pretty happy at around 60 hertz, and all of a sudden we have a series of thermal generators that trip offline, causing our frequency to drop to around 59.9. This is a sizable disturbance. Again, you might think 0.1 doesn't mean a whole lot, but that is actually sizable in terms of when we get into system reliability. When a disturbance occurs, a series of corrective actions occur. And an advantage of traditional thermal generators is they, quote unquote, have spinning mass or inertia, which functions as a system shock absorber. Again, these spinning masses have an inertia associated with them. As I say, inertia is spinning mass, you can think of. They don't like it when they notice speed drops. Again, just from Newton's laws, they tend to fight these changes is what happens. That's part of the value from them. I like the analogy NERC provides of a spinning bike wheel, where there's a bike wheel that's spinning really fast, and you take your hand and press it against it. The bike wheel tries to fight that change. That's a perfect analogy for what these spinning masses do. Now, just a quick discussion of solar resources. Solar resources and things along those lines, they're not directly coupled to the grid in terms of spinning mass. You can proxy it with something called synthetic inertia, but your system operators tend not to like that as much. So I don't want you to come away with the impression that solar is useless in terms of restoring frequency. It's not. It certainly can help, but again, it's a little bit more of a multiple steps through power electronics, through how it actually helps during situations of disturbances, and how we use the inverter potentially with these things as well. So again, just keep in mind that synthetic inertia is not real inertia, and that's why we a lot of times like these spinning masses. They have a lot of value from a reliability perspective. So we've had a disturbance. And what actually happens now? We saw the disturbance. We dropped from about 60.002 to about 59.9. Within seconds, the generator governors, which are on our spinning thermal units, sense the drop in frequency. So the first thing is the generators just naturally try to fight the change, right? That's Newton's laws. But what happens is then again, within seconds, the governors sense the drop in frequency and they start, hey, raise the output, right, through the control mechanisms. That's, again, the governors that do this for us. They don't actually bring us back to where we need to be, though. Okay, so again, we can think of this. The generators first stop the bleeding, you might say, if you got to think of an open wound, and then they try to partially throw some quick bandages on it. That's the generator governor saying, hey, we've got a problem. But it's not enough because the control mechanism for the governors isn't intelligent enough to tell how all of them should work together. This goes into the fact within minutes, generators in the area raise their output based upon the supervisory control and data acquisition systems, also known as SCADA, in terms of automatic generation control, known as AGC. So the AGC now is going to help bring us online over time period and bring us up to where we need to be. Again, this is kind of where the governors catch us in this area over here, and now our automatic generation control is in here trying to bring us back up. Over the long term, if we need to get into reserve deployment, let's say there's not enough generators online, this goes into tertiary control where we might have spinning units that can be sunk at quick notice to be brought online. So again, that's the various phases. We have the inertial response, which is, let me get my cursor over here. This is where this is the physics of the generators themselves. They don't like that change. This is our shock absorbers. Then we go into the primary control. This is, again, our governors. Secondary control, this is where things get smarter. This is the AGC. And then finally, tertiary control, which is basically things along the lines of reserve deployment. We're not going to spend much time on this here. This is kind of time error correction. This is kind of, you can almost think of this kind of like a leap year correction where you have to get everything resunk. This goes into the time control and how we do that. Again, that's a finer point of nuance, which is, as I say, definitely a tertiary point, which we're not really going to spend any time on here. This was a little bit more of a technical discussion, and we are going to need all of these terms as we get into more resource planning. And I'm going to remind you of these as we go along, so don't worry. It's not like I'm going to just expect you to instantly remember everything. But I didn't want to introduce these concepts before we get into our primary goal, which really is electric resource planning. So in our next discussion, I'm going to go ahead and go into this. We've kind of danced around it, but I'm going to start giving you a picture for what electric resource planning is and what it isn't. That's going to round out our three-part series here of this kind of introduction to the fundamentals of the electric grid and a very brief introduction to the electric system planning. And after that, we're going to start diving into the specifics of my world, which is things like nodal market simulations, integrated resource planning, project lifecycle costing, and rates and tariff design as well. We'll spend some time on that. We'll also get into things such as independent system operators, utilities, and regulated and deregulated markets. It's a very broad world we have, and as I say, we could spend years on it and still only scratch the surface. So I'm going to try to dive into the most pertinent topics. Again, as a quick reminder, please go ahead and reach out to me. Here, my email address is right here. It's going to be below in the YouTube description as well. And add me on LinkedIn as well if you ever want to have a discussion or anything along those lines. Please comment in the area below if you think maybe I botched something up in my explanation. Again, it's I always learn something new each day, so please let me know if I made an error. Or perhaps you have questions. You can reach out to me directly or comment in that area below, and I will or someone else on Ulteig's team will respond. I thank you so much, and we look forward to seeing you soon.